How much heat is required to vaporize 175 grams of ice at negative 15 degrees Celsius? So this is a heating curve problem, and it's basically just asking for how much energy you need to put in to go from the solid phase, which is the ice, up to the gas phase. So the first thing you want to do is to draw your heating curve, and I think this makes it easier to visualize where you're starting at and where you need to go and the proper calculations you need to do to get there. So heating curves always follow the same shape no matter what compound you're dealing with. And so the first line is a solid. This horizontal line is solid to liquid, then liquid, liquid to gas, and then gas. And then temperature is here. And then you just have time. So we are starting with ice at negative 15 degrees Celsius. So that is in the solid phase, and you can really put this anywhere on the solid phase. It doesn't really matter. I'm just going to mark it. Oops. That's right there. I'm also going to mark that water melts at 0 degrees Celsius and it boils at 100 degrees Celsius. And these are just two values you should know for water. If you're working with a different compound, the temperatures are going to be different and they'll be given to you. Water's the only one you really need to know. And then next, we're just going to figure out what we need to solve for in this problem, so the different segments. So we have to first get all the way through the solid phase, so we have to solve for this little bit here. That's step one. We have to calculate the solid to liquid transition. We have to calculate the liquid phase. And then lastly, we need to do liquid to gas, and then we get in the gas phase. So those are the 4 steps that we're going to need to do and then add together. And there's 2 equations we'll need for this problem. It's Q equals mc delta T and Q equals n delta H, or Q equals m delta H. And that you can use either one. It just depends on your units that your delta H values are given in. So here they're given in moles. So we can either convert these to grams, or you can convert the grams given into moles. But we'll get to that when we get to that segment. So step 1, we are going to use this first equation, the Q equals mc delta T. That's always what you want to use when you're in a phase on kind of the diagonal lines. So we have Q equals the mass, which is given as 175 grams, times the specific heat, and we're in the solid phase, so we want to use C solid, which is 2.09 joules per gram degrees Celsius, and then times the change in temperature, which delta T is T final minus T initial. So our T final is 0 degrees where we have the phase transition, and our initial is negative 15. So we have 0 minus negative 15 degrees Celsius. And so when we multiply those, we get 5.49 kilojoules, but your answer is really in joules. It's 5,486 joules, but I just converted that to kilojoules because it makes the number a little bit smaller. So now we're on our second calculation, which is the solid to liquid phase transition. So for our horizontal lines, we use the second equation, and I remember that because it's a horizontal line, so there's no change in temperature, and these equations don't have a delta T in them. So our delta H values are given in kilojoules per mole. So I'm going to convert the 175 grams of water given to us to moles. So 175 grams divided by the molar mass, which is 18 grams times 1 mole, equals 9.7 moles of water. So we are going to plug that in for Q equals 9.7 times delta H of fusion, which fusion is the same word as melting, and this is kilojoules per mole. And when you multiply that, you get 58.3 kilojoules. This one is already given in kilojoules, so we don't have to convert our answer. So now, step 3, we're on the liquid phase. So we go back to this first equation, and we have Q equals M, which is the mass, so 175 again, times C. Now we use the C liquid, which is 4.184 joules per gram degree, and then times our delta T, which our delta T is, our initial is 0 degrees and our final is 100, so that's 100 minus 0 degrees Celsius, and this comes out to be 73220 joules, which is equal to 73.2 kilojoules. And so now, last step, step 4, the liquid to gas transition, which is Q equals our moles of water, so 9.7 times delta H of vaporization, which is given as 40.7 kilojoules per mole, and that equals 394.8 kilojoules. So we solve for each of these 4 steps on the heating curve, and so Q total just equals Q1 plus Q2 plus Q3 plus Q4. So when we add all 4 of our answers together, which are all in kilojoules, it gets us 531.8 kilojoules. And that's how much heat it takes to get ice at -15 degrees all the way to the gas phase.